A lot of the things we looked at in Unit 1 or Chapter 1 covered some aspects of Unit 2 and then a little of Unit 3. So what we are going to be doing today basically is very simple. Today we will look at, we'll look at the arithmetic logic unit, which is one major component within the central processing unit, which is very important. Now, if you remember in our previous lecture, we talked about the functional units of the computer, where we mentioned that the functional unit comprises of the input-output units. We talked about the functional unit having the input and output units, the memory, and then we had the processing unit or the processor, where we had the ALU and then the control unit. So today, majorly, what we are going to be looking at is the arithmetic logic unit, since we are looking at computers at the basic level, where they will just be performing arithmetic operations. So the arithmetic logic unit is basically a digital circuit, okay? It's a digital circuit which is capable of performing arithmetic and logical operations. So when we talk about its capability of performing arithmetic operations, we are talking about basically addition, subtraction, division, multiplication, etc. And then when we talk about logical operations, we are looking at operations that are performed using logics or logic gates, okay? So the ALU is responsible for the performing of mathematical calculations such as addition, subtraction, multiplication, and division, as well as some logical operations such as the AND, OR, NOT, and XOR gate or XOR operations. Now, the ALU, because of its capability of performing logic operations, accepts inputs in the form of binary. It also produces outputs as well as in the form of what? Binary. And most computers today, you would find them using arithmetic logic units or components within the CPU. And this also enhances the performance of computers. So that is basically what an arithmetic logic unit is. And like we said earlier on, the arithmetic logic unit is capable of performing integer arithmetic operations, bitwise logic operations like the AND, the NOT, OR, and XOR. And then also, it is capable of performing bit shifting operations, where it shifts or rotates a certain bit either to the left or to the right. Okay. So this is basically an extension of digital electronics. Now, for the arithmetic operations, we already know all of them in terms of addition, multiplication, and all that. Those ones are easy to do. Now, let's look at the logic or bitwise operations and see how these are done, or the principles behind those ones. So before we can appreciate that, we would need to understand the various logic gates and how they operate. So the first one we'll look at is the NOT gate. The NOT gate. The NOT gate is basically a single input, a single output logical device, where the output is basically a complement or a complementary of the input. What this means is that since we are dealing with binary, we would normally have inputs to be bits, either zeros or ones. And so if the input to a NOT gate is 1, the output will be 0. If the input is 0, the output will be 1. That is the logic behind the NOT gate. And this is mostly used in switches. So in instances where you want to design an automatic switch, let's take, for instance, you have a house where you're trying to secure the house. And so you have a laser beam instead of a wire on top of the fence. You have a laser beam. And then anytime there is something crossing the laser beam, this laser beam is connected to a system which behaves like a NOT gate. So once there is continuous laser to that system, the output will remain low because the input is high. But immediately there is a break in the laser beam, then you would have the output going high because the input is low. So that is the logic with the NOT gate and an example of how it can be used. Okay. Now let's also look at another one which is called the AND gate. The AND gate. Now the AND gate is basically a 2 input and a single output logic device. Now the AND gate performs an operation which is identical to multiplication. So here, with this image you see here, which is the diagram or the illustration of an AND gate, you have input 1 and input 2 and then output. Now, because this is 2 bits, what this means is that we're looking at 2 raised to the power 2, and that will give us 4. So it means we would get 4 possible combinations of 2 bits. So when you look at the truth table, you see you have 0, 0, 0, 1, 0, and then 1, 1. These are the possible combinations of the inputs to the AND gate. So the AND gate would produce an output of 1 only when the inputs are identical. Where the inputs are not identical, the output will always be what? 0. So when you look at this truth table here, you would notice that the inputs are, wherever the inputs are identical, I mean 1, 1, you would get 1. But when it is 0, 0, 0 times 0 will give you 0, 0 times 1 will give you 0, 1 times 0 will give you 0, 1 times 1 will give you what? 1. So this is basically how the AND gate operates. Now, where can we apply the usage of this AND gate? You may have a system where you want to always monitor the outputs to a certain system. Let's take, for instance, you have a plant or you have an installation where you feed it with 2 separate sources of power. And at every point in time, you want to ensure that you know the state of these 2 sources. So once the 2 sources are available, you should get an output. You can apply the logic of an AND gate, or you can implement an AND circuit to achieve that. Then also, we look at the OR gate. The OR gate is also a 2-input, 1-output logic device, which means that it will also have 4 possible combinations of inputs and the outputs Y as usual. Now, the OR gate behaves like, or it behaves with the principle of addition. So there would always be an addition between the 2 bits. So when you look at the truth table, you would see that whenever we have 0, 0, the output is 0. But when we have 0, 1, the output is 1. 1, 0, the output is 1. 1, 1, the output is what? 1. So you take note of that. That is how the OR gate also operates. Then we have the XOR gate. Now, the XOR gate, which also has a 2-input, or it's a 2-input device and a 1-output device, produces 1 as an output only when the inputs are different or they are non-identical, they are not the same. So in an instance where you have the inputs being 0, 0, you have 0, 0, 1, you would get 1, 1, 0, you would get 1, 1, 1, you would get 0. Okay. So also understand that bits 0 represents off or low, and bit 1 represents on or high. So basically, these are how the various logic units or logic gates operate. Now, arithmetic logic units, like I said earlier on, can be designed to perform very complex calculations or operation. And in so doing, most of the time, what happens is that as engineers, we don't just look at the output. You also look at the fact that whatever it is that is being produced, it will not be too expensive and there will not be a compromise on efficiency. Okay. All right. And then also there is that constraint of power usage. So the more complex an arithmetic logic unit becomes, it dissipates a lot of power, or it consumes a lot of power, which in effect can make it more expensive to use. Okay, so these are some cautions. Now let's look at some complex operations that arithmetic logic units are capable of performing. One, simple calculations in a single clock, calculation pipeline, where you have calculations being performed concurrently. Then we have interactive calculations where, as calculations are ongoing, there will be the need to feed it with an input midway through the calculation and all that. It also allows for coprocessor processing, okay? And then ALUs also feature in software libraries and allows for easy programming. So these are some complex operations that ALUs are able to perform. And like I said earlier on, the inputs to the ALU are the data that we would normally work on, which we normally call the operands. Okay. And then they would always give us an output as the result of whatever computation that has been performed. Now, there is something you need to know, or you would need to understand. So long as we have ALUs, or arithmetic logic units, which are capable of performing integer arithmetic operations, then there will be the need to have another processing unit which is used to perform operations on what we call floating points. Okay, so floating points are basically numbers that have decimal points. So for instance, 2.14, 5.13, or 101.10. These are floating points or floats. So in order to perform operations on these, we use what we call floating point units. So a floating point unit also performs arithmetic operations between floating values or between two values which are floats, okay? And in order to do that, the FPU is what does that. This is an assignment for you to go and read. It's not an assignment that you would submit. It's for you to go and do extra reading on that to try and understand what fixed point number operations are and what floating point number operations are. So please take your time and then read about that. And these are the numbers that are normally operated upon using FPUs. Okay. All right. Now, one last thing I would want us to look at before we bring today's session to an end is to highlight a little bit more into the instruction cycle. You remember we talked about the execution of instructions, where we said that instructions are mostly or ordinarily will be kept within the memory, and they would only be fetched into the processor when there is the need for processing. So when we talk about the instruction cycle, we're basically talking about the cycle where instructions are fetched from the memory into the processor, they are decoded, and they are executed. So these are the three phases of any instruction cycle. So please take note of that. That is the fetch cycle, the decode cycle, and the execute cycle. So if you take this diagram, for instance, you will see that in the execution of a code, it starts with the fetch of the instruction. Then the instruction is decoded. Then after the decoding of the instruction, if there is an operand that needs to be fed or fetched, the operand is also fetched and decoded, and then execution takes place. So this is basically the basic instruction cycle, which has three phases. That is the fetch cycle, the decode cycle, and the execute or the execution cycle. So basically, this is what we needed to look at today. So at this point, if there are any questions, you can feel free. Just use your, what do we call it? Your reaction and raise your hand. I'll give you the option to talk, and then whatever question you have, you can ask. No questions. I would want to believe whatever I handled today was too easy to understand. So you do not have. Yes, Bilal.
Yes, please. This last part, I didn't really understand this last part. That's the reason why I couldn't even ask a question.
Which last part?
The basic instruction cycle.
Okay, so do you remember in our previous In our previous lecture, we talked about the fact that there is a connection between the processor and then the memory.
Yes.
Okay. And can you imagine that diagram?
Yes.
Where you have the memory on top, and then you have the processor down, and then you have a bidirectional connection between the processor and then the memory. And within the processor, you have the MAR, the MDR, and then the instruction register, as well as the program counter.
Yes.
Now, what we are basically saying here is that in the execution of any instruction, so assuming you have a program or a set of instructions which collectively becomes a program, anytime there is the need to execute any of those instructions, there are three phases to the execution. And these three phases together is what we call the instruction cycle. So the first phase is that the instruction will be fetched from the memory and brought into the processor. That is phase one. Phase two would be that the instruction will be decoded. And then phase three, the instruction will be executed. So these are the phases of every instruction cycle. I don't know if this now makes clear or makes it clear.
It's clear now.
It's clear now.
Now I understand. Thank you.
Okay. All right. Yes. Daniel. Daniel, your hand is up.
Yes, sir. Sir, please, my question is that the NOR gate and the OR gate, isn't the truth that the truth table is still the same?
No. Which gate and which gate?
The NOR gate and the OR gate.
Okay, let's see. Let's go back there and see if indeed they are the same. So we have a NOT gate, isn't it?
Yeah.
And we're saying that the NOT gate has only one input and one output. And since we are dealing with binary, the input could either be a 0 or it could be a 1.
Yeah.
So since it is just a one input device, that will be 2 raised to the power 1. And that will give you two possible combinations. That is why we would either have an input to be 0 or an input to be what? 1. And we're saying that the NOT gate will give you an output which is the opposite of the input. Okay, so if you look at this truth table, if the input to the NOT gate is 0, you get an output of 1. If the input is 1, you get an output of what? 0.
Okay, sir.
Please, do you understand it now?
Yes, sir.
What was the other gate you were talking about? Is it the OR gate?
Yeah, the OR gate.
So now here, the OR gate, the difference is that the OR gate basically uses the principle of addition.
Okay.
So the addition of binary, if we add 0, 0, it is 0. If we add 0 to 1, it is 1. If we add 1 to 0, it is 1. If we add 1 to 1, it's 1. Please, you understand?
Yes, sir.
That is the principle. So the NOT gate and then the OR gate are not the same. They operate with two different principles. The NOT gate would give you an output which is opposite to the input. But the OR gate would give you an output after performing a binary addition on the two inputs. Okay?
Okay, sir. Yes, sir.
All right.
So, but the AND gate and the OR gate, we say they are the same, but is it AND gate, is it for like multiplication and the OR gate is addition?
The OR gate uses the
Yeah.
principle of addition.
Yes, sir.
And then the AND gate uses the principle of multiplication.
Okay, sir.
Are you okay now?
Yes, sir.
Okay. Any other question?